Good day, students. I welcome you to your favorite YouTube channel, Physics for Everybody. Today, we'll be solving questions on 2023 October-November Cambridge IGCSE Physics 0625 examination, paper 2, variance 3. Okay? Yeah. And if you want to reach out to me for personalized tutoring, you can send an email to me. Here, my office is in Lekki, Lagos, Nigeria. Without delay, let's go straight to the question. Question number 1. How many of the quantities shown are scalars? You have mass, momentum, density, and energy. Mass is a scalar quantity because its direction does not matter. Momentum is a vector quantity because momentum is mass multiplied by velocity. Velocity being this vector quantity simply makes momentum a vector quantity. Density is a scalar quantity, energy is a scalar quantity. Since these three are scalar quantities, then C is the correct answer, which points as 3. Question number 2. A train is on a straight track. The graph shows how a quantity y varies with time. Which statement can be true? Which of these statements can be true? Let's look at the first one. The train is stationary and y represents the distance from the last station. Okay, if the train is stationary, then it means distance is not increasing with time. Yeah, so drawing a horizontal line, okay, for a distance time graph simply means distance is not increasing with time. So this means the train is stationary, okay? But since this line is not on zero, if this line was on zero, then it's talking about the start time, okay? But since this line is not on zero, that means the train had already traveled some distance initially before it eventually comes to rest, okay? So which makes this statement correct, okay? Because y represents the distance from the last station. So the train had traveled to a station, then it stays at rest at that station. You get it? If the train had not traveled initially, then the horizontal line would be at the zero, at the origin, okay, meaning that no distance had been traveled initially. So number 1 is correct. Let's look at number 2. The train is moving and y represents the distance from the last station. If the train is moving and y represents distance, then we'll have a slant gradient, okay, not this horizontal line that you had. So number 2 is not correct. Number 3, the train is stationary and y represents the speed of the train. If the train is stationary, yes, if this is speed and the train is stationary, if y represents the speed and the train is stationary, then this does not mean the train being stationary, okay? It's only when the line is on the origin that we know that it means the train is stationary. Why? Because speed at the origin is 0, okay? That's what this 0 tells you, this 0 here. It tells you speed at the origin is 0. But at this point, speed here cannot be 0, so this does not mean that the train being stationary, okay? So the train cannot be stationary when the horizontal line is here. I believe that is understood. Let's look at the last one. The train is moving and y represents the speed of the train. Well, if the train is moving, yeah, so this shows that the train is moving at a constant velocity, okay? So you can use y to represent the speed and then the train is moving, fine. But you know it is moving at a constant velocity, okay? Good, it's moving at a constant speed. The speed is not increasing and the speed is not decreasing. So this one is also correct, okay? That makes 1 and 4 the only correct option, which is option B. We go straight to question number 3. The diagram shows a speed-time graph for a moving object. Speed, time. The diagram shows an exponential line. Let's see, is a curve. Which description of the object's motion is correct? A, decreasing acceleration. Excellent. If acceleration was increasing, the curve would look like this. Okay, it would be an exponential rise. But here, the curve was rising and then the slope, the gradient of this line began to decrease. It continues to decrease till it eventually becomes 0, where we have a horizontal line. Okay, so that simply means acceleration was high here, okay, and acceleration began to decrease till acceleration becomes 0. Okay, and if acceleration decreases further, then acceleration will become negative and the slope begins to go downwards this way. So yeah, it shows decreasing acceleration. A is correct. We don't need to check B and C. The mass of air hitting the blades of a wind turbine each second is 1.5 times 10 to the power 4 kilogram. The speed of air is 4 meters per second. The density of air is 1.2 kilogram per meter cube. Which rho gives the volume of air hitting the blades each second? We are looking for the volume per second. Okay? And the kinetic energy of air hitting the blades each second. How do you get the volume of air? You know, the formula for density is mass divided by volume, right? Good. Density is mass divided by volume. So we apply that here. So density equals to mass divided by volume. That simply means volume equals to mass divided by density. What's the mass of the air? 1.5 times 10 to the power 4. What's the density of air? 1.2 kilogram per meter cube. So we divide 15,000 by 1.2. 15000 divided by 1.2. Okay, so we have the volume of the air as let me divide 15,000 by 1.2. 15,000 divided by 1.2. 12,500 kilogram. Sorry, meter cube. 12,500 meter cube. So two significant figures, okay, since all the values are given to two significant figures. So we expect this to, in two significant figures, that will be 13,000 meter cube. Now, they also request for what? Kinetic energy. What's the formula for kinetic energy? Kinetic energy equals to half mv square, okay? Where this v is the velocity, okay? Yeah, this second v, the small letter v represents velocity. The capital letter V represents volume. The capital letter V is the volume of air, right? Good. So now to calculate kinetic energy, half times mass. The mass is 15,000 multiplied by the velocity. Okay, that's the speed. Speed of air. Speed of air is 4 meters per second. So multiplied by 4 square. 4 square is 16. 16 multiplied by half give us 8. So you just have 8 multiplied by 15,000. 15,000 times 2, 30,000. 15,000 times 4, 60,000. 3,000 times 8 will be 120,000. Okay, so yeah, that's it. Joules, rather. So the volume is 13,000 meter cube. The kinetic energy is 120,000 joules. Which option gives us 13,000 and 120,000 joules? That's option B. So we select 13,000 for volume and 120,000 for kinetic energy. We go straight to question number 5. An object moves in a circle at constant speed. Which statement about the force needed on the object is correct? Okay, this must be talking about the concept of centripetal force, okay, for an object moving in a circular path, centripetal force. Yeah, centripetal force. Let's see. The force away from the center of the circle keeps the object moving in a circular. No. The center must, the direction of the force must be towards the center. The direction of the force must be towards the center of the circular path. Okay, the force in the direction of motion of the object. No, not direction of motion. The force does not go in direction of motion. No, that's wrong. Option C, a force towards the center of the circle keeps the object moving in the circle. That's correct. That introduces the concept of centripetal force, okay? Centripetal force equals to mv squared over r. Yeah. So that's it. The direction of centripetal force is towards the center of the circular path. Number 6, a uniform rod rests on a pivot at its center. The rod is not attached to the pivot. Forces are then applied to the rod in 4 different ways, as shown. The weight of the rod can be ignored. Which diagram shows the rod in equilibrium? For an object to be in equilibrium, the resultant clockwise moment must equal to the resultant anti-clockwise moment, okay? And the resultant, or you just say the resultant moment must equal to zero. The resultant forces must equal to zero. Let's see, anti-clockwise moment, these distances look equal, these forces are equal, okay? So, and these forces will be balanced by the reaction here. So that means this object is in equilibrium here. The next one, these two forces tends to move the object upward and is not balanced by any other force, okay? Take note that the rod is not attached to the pivot. The rod is not attached to the pivot. What does that mean? That means in this case, the rod just keeps moving upward because there's nothing balancing it. But in this case, the rod cannot continue to move downward because the pivot here balances it. Here, the rod just continues to rotate in a clockwise direction. And here, the rod will also rotate in a clockwise direction. Why? These two forces cancel each other, but there's a resultant force here in this direction. So it continues to rotate in a clockwise direction. So A is the only correct answer to that question. We go straight to question number 7. A car of mass 1,200 kilograms is traveled along a straight horizontal road. Which impulse is needed to accelerate the car from 5 meters per second to 10 meters per second? Now, what is the formula for impulse? Impulse equals to mass multiplied by change in velocity, okay? Or you say mass multiplied by final velocity minus initial velocity. What's the mass of the car here? The mass of the car is 1,200 kilograms. The final velocity, that's the velocity at the end, 10 meters per second, minus initial velocity in the beginning, 5 meters per second. So you have 1,200 multiplied by 5 because 10 minus 5 gives us 5. 12 multiplied by 5 is 60, then that will be 60, which is 6,000. Then the unit of impulse is Newton seconds, or you call it kilogram meters per second. So you have 6,000 Newton seconds, which is option A. We go straight to question number 8. A mass bounces up and down on a steel spring. The diagram shows the mass and the spring at different points during the motion. Highest point, mass moving downwards. Lowest point, mass moving upward. Okay, so it shows that the mass continues to oscillate while attached to the spring. At which point is the least energy in the gravitational potential store of the mass? And at which point is the most energy in the elastic store of the spring? Let's see. Least energy in the gravitational potential store, mass moving down. Least energy, mass moving down. No, not here. Gravitational potential energy is least when the object is at its lowest point. Yes, gravitational potential energy is least when the object is at its lowest point. Okay, yeah, because gravitational potential energy is mgh. Okay, yeah. So this is the height here. Here, this is the height here. Here, this is the height here. So this is even where we have the highest gravitational potential energy. And here, gravitational potential energy here is least, okay? If you take this as the reference point, okay? Yeah, and if you even take a point like this as the reference point, yes, gravitational potential energy is also less here because the height here is small in comparison with the height in other cases, okay? So that simply means gravitational potential energy is least at this point. Gravitational potential energy is smallest. Most energy in the elastic store of the spring. Where do you have most energy in the elastic store? That is when the spring is stretched the most. Okay, when the spring is stretched the most. And where do you have the spring being stretched the most? It's also here. Look at the spring. You see how stretched it is. The load has stretched the spring completely. Okay, so that makes D the correct answer. Lowest point, lowest point. That makes D the correct answer to question number 8. Go straight to question number 9. A boy uses a rope to pull a boy uses a rope to pull an object of mass m up a slope. The rope is parallel to the slope. The tension in the rope is constant and of value F. To solve a question like this, I like to draw diagrams. So this is the load. Yeah, so a boy uses a rope to pull an object of mass m. This is the mass of the object, and this is the rope. The tension in the rope is constant and of value F. Tension in the rope is of value F. The object moves a distance d along the slope and rises to a height h. It moves a distance of d along the slope and rises to a height h. That means this is the vertical height, okay? This is the height h. If we take, let me use color red for the ground level. If we take this as ground level, then this is the height to which the object has risen. Yeah, so the object has traveled this distance d, okay, from here to here, travels distance d, and in that process, it rose through a height h. The object moves a distance d along the slope and rises to height h. That's correct. How much work is done by the boy? Well, the work done by the boy is the force multiplied by distance. Work done is force multiplied by distance. Okay, what's the force here? The force here is the tension in the rope. Yeah, tension is the force in cords or ropes. So the force here is F, okay, and the distance is the distance traveled by the boy, okay, and the boy has traveled this distance D in the direction of this force. So that's why I'm using this distance D. We are not using height H. Okay, height H is when we are considering the weight of the boy here as the force. But the boy is not lifting the object vertically, he's pulling it along this slant inclined plane. So it's the force along the inclined plane multiplied by the distance traveled along the inclined plane. That's why we're using F times D, which makes A the correct answer to question number 9. Question number 10. A microwave oven is rated 900 watts. Which statement correctly describes the meaning of this value? Watts. 900 joules are transferred every second. Correct. Why? Because power is measured in watts, and the formula for power is energy. Power is energy divided by time. What is the unit of energy? Energy is measured in joules. Time is measured in seconds. So what is joules per second? Okay. So 900 joules are transferred every second, joules per second. A is the correct answer to question number 10. We go straight to question number 11. An object is immersed in a liquid of density rho, this is density. The pressure at this depth due to the liquid is P. The gravitational field strength is G. What is the equation for the depth h of the object beneath the surface? And you know the formula for pressure in liquid is that pressure equals to density times gravity times height. They now ask you that what is the equation for the depth h? How do you get the depth? You make the depth the subject of the formula. So h is the depth, okay? We make h the subject. How do you make h the subject? Divide both sides by density times gravity. Divide both sides by density times gravity. Divide this one by density times gravity. So that means H2 will cancel out, G will cancel out. You'll be left with H. That simply means H equals to pressure divided by density times gravity. This is the formula we are looking for. The formula that gives us the height, okay, or depth here. So where do you have density divided by gravity? Height equals to pressure divided by density times gravity, which makes option C the correct answer to question number 11. We go straight to question number 12. A sealed bottle of constant volume contains air. The air in the bottle is heated by the sun. What is the effect on the average speed of air particles in the bottle and the average distance between them? If the bottle is sealed, right? Good. So if temperature is increasing, what happens to the average speed of air particles? As temperature is increasing, it means the kinetic energy of the particles increases. And as kinetic energy is increasing, it means the speed is also increasing. Okay, so that simply means the average speed of the particles will be increasing. What about the average distance between air particles? Take note that it's in a bottle and the bottle is airtight. Let this represent the particles of the gas. If you increase temperature, okay, by heating it, in this case, the heating is coming from the sun. If you increase temperature, the particle only vibrate faster, okay, they only travel faster, but you are not increasing the distance between them. The only way to increase the distance between this particle is by making this bottle bigger. Okay, yeah, if it was a balloon or an elastic container, an elastic vessel, then you know that if you are increasing the temperature, the kinetic energy of the particles will increase, then volume have to increase in response to that. But since volume is not increasing, since is not an elastic material, then the distance between these particles remains the same. Okay, that makes B the correct answer to question number 12. We go straight to question number 13. In an experiment to investigate the relationship between the volume of a sample of air and its pressure, the volume of the sample the volume of the sample is decreased. Volume is decreased and its pressure is measured continuously. Curve X on the graph shows the results that would be expected for a fixed mass of air at constant temperature. Curve Y shows the results that are obtained in this particular experiment. Okay, so this is what we are expecting. Okay, yeah, this is what we are expecting because volume is decreased and pressure is measured. Since volume is decreasing, that simply can be considered as a situation like this. You have air trapped in a container and then you have a piston, okay, with which you can apply a force. Now, when you push, let's assume these are air molecules. Now, when you push the piston downwards in order to reduce the volume, okay, because that's what the question says, the volume of the sample is decreased and its pressure is measured continuously. When you press it down in order to decrease the volume here, okay, so let's assume after pressing it down, the position of the piston is here. What do you think will happen to the air particles? You think they will still be scattered? No, they will gather together. Okay, they will gather together. That simply means pressure will increase. And that's what we have here. As volume is decreasing, pressure is, as volume is decreasing, pressure is increasing. And if I increasing volume, pressure will be reducing. Okay. Now, but curve Y shows the results that are actually obtained. This is what we were expecting. This is what we were expecting. But this is what we got. This is what we got. What could be the reason why we didn't get what we were expecting? That's what they are asking you here. Which row shows two possible reasons why curve Y is different from curve X? Okay, yeah, question number 13. A, the temperature of the air increases as the volume is decreased. Yeah, if temperature is increasing as volume is decreased, what does that mean? If as volume is decreasing, temperature is increasing, it simply means pressure will be increasing. Okay, okay, so it's supposed to look like this or even worse than this, not coming up to this level. Okay, let's see the next one. The temperature of the air increases as the volume is decreased. No, it's not that. Let's see the third option. The temperature of the air decreases as the volume is decreased. Yeah, if you are decreasing the volume and pressure is rising and it goes this way. But if you are decreasing the volume as pressure is rising and is going this way, then reducing the volume would make pressure be lower. Okay, it's reduce the pressure lower further. So this is the curve you get if as you are reducing the volume, you you decrease the temperature. This is the graph you get. Let's see the second part. Air air leaks into the container as the volume is decreased. No, no, no. If you are decreasing the volume, air cannot be leaking into this container. No. Probably air is leaking out of the container. Okay. Air leaks out of the container as the volume is decreased. That's correct. That makes D the correct answer to question number 13. We go straight to question number 14. The student splashes water onto her face. Here are three statements about the effect. A. Water uses energy to evaporate. Correct. That's cooling by evaporation. Water gains thermal energy from the student. Yes. The water that will evaporate will receive thermal energy from the student's face. Okay. The face of the student cools. Yeah, that's cooling by evaporation. That's correct. Okay. Yeah, so does it mean P, Q, and R is the correct answer to question number 14? Let's see. P and Q only, P and R only, Q and R only, P, Q, and R, D. That makes option D the correct answer to question number 14. We go to question number 15. Four containers each contain water. More water at the same temperature is added to each container. For which container does water now evaporate more slowly? Does water now evaporate more slowly than it did before? So that's the emphasis. Consider the rate of evaporation before. Consider the rate of evaporation after the water has been added. Which one will be lower? Now, I want to consider the rate of evaporation here. Now, I want to add water to it so that the volume of water will increase. Let the volume of water increase. Volume of water increases. Volume of water increases. In which of these containers do you think water will now evaporate more slowly? Here, there's no mention. Factors that affect the rate of evaporation are temperature, um, surface area. Okay, number one is temperature. Number two is surface area. Number three is humidity. Okay, if the air is dry, evaporation will be faster. And number four, um, wind. Yeah, if you have air, if you blow air over the surface of the liquid. So these are the four factors that affect the rate of evaporation. There's no mention of temperature, there's no mention of surface area, there's no mention of humidity, there's no measure of wind. You just talk about you adding water. But look at the shape of this container. What factor do you think is changing? Is surface area. So let's focus on surface area. Here, as you're adding water, surface area of the water does not increase. Here, as you're adding water, surface area of the water increases. That means the rate of evaporation will increase here. Evaporation will take place at a faster rate here. See, as you're adding water, the container gets narrower. That means the rate of evaporation will be reducing in this one. Here, the surface area remains the same as you add water, so the rate of evaporation does not change. This is the only one where the rate of evaporation becomes slower than it did before. That makes option C the correct answer to question number 15. We go straight to question number 16. A cupboard is placed in front of a heater. Air can move through a gap under the cupboard. So there's a gap here for air to flow through. Which rule describes the temperature and the direction of movement of air in the gap? Direction of movement. This is the heater. This is cupboard. This is the space. That means air can move in through this gap. If air is moving in through this gap, okay, when the air gets here, what happens? It gets heated, temperature rises. When air is heated and the temperature increases, the air expands or it gets lighter, okay, meaning the density of the air will reduce. So the air will be able to rise. Okay, so that will be the convection current in this case. Okay, cold air going, it gets heated, it rises to the top so that another cold air can come in. This will be the structure of the convection current. Let's see which row describes the temperature and the direction of movement of air in the gap. Air temperature, cool. Air direction, okay. Which row describes the temperature and the direction of movement of air in the gap? In the gap, this is the gap. So what kind of air is moving into the gap? Is it cool air or hot air? It is cool air, okay? Cold air goes in, okay? The cold air that goes in is cool. Direction, away from the heater, no. Towards the heater, correct. Cool air goes towards the heater. This is the direction of movement in the um air gap. Okay, our focus is in the air gap, so that makes B the correct answer to question number 16. Go straight to question number 17. Light diffracts when it enters a telescope. This causes the image to blur slightly. The amount of diffraction depends on the diameter of the hole through which the light enters the telescope and the wavelength of the light. Which combination for diameter and wavelength will result in the sharpest image, least blurring? Which combination will result in the sharpest image? That's which one will cause the least blurring? Let's see. Diameter of what? Diameter of the hole. Okay, then wavelength of the light. Let's see. And take note that diffraction happens in, in waves when the size of this opening, okay, in this case the size here is the diameter, okay, and the wavelength, when the wavelength is equal to the diameter, diffraction will be maximum. Okay, yeah. But when the diameter is smaller than the wavelength, fine, there will be diffraction. But the rate of diffraction will be maximum when both of them are equal. Okay, but when the size of this gap, when the diameter of this gap is far larger than the wavelength, there will be no diffraction. Which combination for diameter and wavelength will result in the sharpest image? Okay, we have the sharpest image when there is no wavelength, when there is no diffraction. And for there to be no diffraction, the size of this gap will be far bigger than the wavelength. Okay, wavelength, that's the distance between two successive crests and top. Okay, yeah, so these are waves. I think I've done 4 wavefronts here. So if the size of this gap is far larger than the distance between these two wavefronts, then diffraction will be minimum and the image will be sharp. So let's see where we have the size here bigger than the wavelength. Large diameter, long wavelength, no. Large diameter, short wavelength. That's good. Large diameter, this one is large, short wavelength. Distance between these two is small. So it is B that we have large diameter and short wavelength. Okay, it is that same B that diffraction will not occur at all. And when there's no diffraction, the image formed will be sharp and not blurred. So that makes B the correct answer to question number 17. We go straight to question number 18. The diagram shows a transverse wave. Now, this is the question. Which row identifies the amplitude and the wavelength of the wave? Amplitude is the easiest. Maximum displacement from the equilibrium position. That is P for amplitude. Okay, P for amplitude. Then wavelength, distance between two successive crests or two successive troughs. That is S. S for wavelength. So where do you have P and S? Option B. That's the correct answer to question number 18. We go straight to question number 19. Question number 19. The diagram shows the effects of a prism on white light. Some light is reflected on striking the prism, and some is refracted and dispersed to form a spectrum. What happens if monochromatic light is used instead of white light? Okay, so this shows the dispersion of white light. White light spread into the different frequencies. Yeah, so you have the spectrum of white light. But if you use monochromatic light, which is only a single frequency, then it will not be dispersed. Only that single frequency would come out at the other end of the prism. Okay, it won't spread the light into the different components because monochromatic light is light of one frequency. So that means there will be no dispersion. There will be no dispersion of the emerging light. Okay, that means D, the correct answer. Yeah, so there will be reflection. Yeah, the changes color as it passes through the prism. The light changes color as it passes through the prism. The most important thing is that there will be no dispersion. That's monochromatic light. The color does not change as it passes through the prism. Question 20. The diagram shows a ray of light incident on a plane mirror. This is the plane mirror, this is the incident ray of light. The angle between the ray and the mirror is 35 degrees. This angle is 35 degrees. The ray is reflected by the mirror. What is the angle of reflection? Well, to get that correctly, we have to produce a normal, okay, which is a perpendicular line to the mirror. Then, if the angle here is 35, how do you get the angle of incidence? The angle of incidence equals to 90 minus 35. Why? Because the total angle here, this square corner is 90 degrees. Okay. Yeah, out of 90 degrees, this one here is 35. Then it simply means the remaining, which is the angle of incidence, will be 90 minus 35. So 90 minus 35 gives us 55 degrees. So that simply means the angle of incidence is 55 degrees. And for the law of reflection, angle of incidence is equal to angle of reflection. Let me use black color to draw the reflected ray. The reflected ray goes this way, and this is the angle of reflection. Okay, angle of incidence equals to angle of reflection. So if angle of incidence is 55 degrees, automatically angle of reflection will be 55 degrees, which makes option B the correct answer to question number 20. Let me turn to blue ink. I like using the color blue to solve. All right, question number 21. A thin converging lens in a camera produces a real image on a photosensitive surface as shown. Yeah, so this should be the photosensitive surface. At which position is the image of the top of the object formed? This is the top of the object. How do you get the position of the image? We know that a ray coming from the top passes through the optical center of the lens and goes straight without being without the change in direction. Okay, it doesn't get deviated. There will be no change in direction. It just goes straight. Then the ray parallel to the principal axis. This is the principal axis. Okay, this ray that is parallel to the principal axis, after refraction through the lens, it will be made to pass through the principal focus. Okay, so it passes through the principal focus and goes up to this point. So where the ray coming from the top, this one coming from the top, this place where it meets this second ray coming from the top, this place where they both meet, this is where the top of the image will be. Okay, so if this is the object, the image will be upside down, okay, because the top goes downwards. So it will produce an inverted image. That's how we got to know that it produces an inverted image. Okay, so image is at point C, which makes option C the correct answer to question number 21. Option C. Go straight to question number 22. Light is traveling through air. It strikes a glass block at an angle of incidence of 45 degrees. The glass has a refractive index of 1.4. What is the angle of refraction of the glass as it enters? What is the angle of refraction of the light as it enters the glass? Well, we have to use the law of refraction, the formula we use to get the refractive index. Refractive index equals to sine angle of incidence divided by sine angle of refraction. And we know refractive index is 1.4. So you say 1.4 equals to sine 45 divided by sine r, because we're looking for angle of refraction. Hence, we can say sine r equals to sine 45 divided by 1.4. Okay, yeah, so sine r equals to, then we check sine 45 degrees. Sine 45 degrees. So let me check it. Sine 45 degrees. Yeah, sine 45 equals to cos 45. Yeah, that's 0.707. That's good. That's correct. 0.707 over 1.4. So that means R will be shift sine. We now take the ratio of 0.707 and 1.4. Okay. 0.707 divided by 1.4. 0.505. So shift sine 0.505. That's what we are doing with the calculator. Shift sine 0.505. So let me do inverse of sine. Let me check this out. Okay, so inverse of sine is not working. Did I press lane? Oh, inverse. I'm supposed to use inverse of sine, inverse of sine 0.5. That gives me 30. Good. So that means inverse of sine, no, inverse of sine 0.505 should give me the correct answer. 30.33 degrees. Write to the two significant figures. That will be 30 degrees. That's 30 degrees. That's my angle of refraction. Which makes option B the correct answer to question number 22. We go straight to question number 23. Which rule gives approximate value for the speed of sound in copper, water, and air? Copper is a metal, so that simply means in the metal, speed of sound should be maximum. Yeah, because sound travels fastest in solids, okay, followed by liquid, okay. So this will be an average value. Then air, the air must be the smallest. So when do you have this trend? Maximum for copper, average for water, minimum for air. Maximum for solid, water, average, minimum, air. Okay, which makes option A the most reasonable answer. We don't have to search too far. We don't have to search the other option. Once we are sure of our answer, we proceed to the next question. Question 24. Which metal can be attracted by a magnet um, from magnetic materials? Zinc, no. Lead, no. Iron, yes. Iron, steel. These are from magnetic materials, okay? Iron. Number 25. The diagram shows an electric circuit. So this is the electric circuit. Yeah, this is the electric circuit. This is the positive terminal, this is the negative terminal. Now the question asks, in which direction do free electrons flow around this circuit? And what quantity does the ammeter measure? How do you know the direction in which free electrons would flow? Let us use our simulation to check this so that it can be clearer to us. So from our knowledge of electric circuits, we know already that current flows from positive terminal, goes around the circuit and returns to the battery through the negative terminal, and current continues to flow that way. And that's what we have here. This is a circuit. Okay, let me click on circuit symbol. This is the positive terminal, negative terminal. Current flows around this way through the bulb and return to the negative terminal, right? Yeah. Okay, what else do we have here? And what if we check the electron? What will be the direction of electron? Electron flow in opposite direction to the direction of current. So electrons come out from the negative terminal, flow through the circuit and return to the positive terminal. And this is the ammeter used to measure current. Okay, good. So electron come out from negative terminal, flow through the circuit and return to the positive terminal. The request for direction of flow of electron is anticlockwise. Okay. Quantity measured by ammeter is the current. Total charge passing through ammeter. Charge passing each point in the circuit per unit time. Good, good. This is the correct answer. Why did I say that? Because current equals to quantity of charge divided by time. Charge per unit time. That's how you get current flowing in a circuit. Okay. Current is defined as charge per unit time, Q over T. Okay, so that makes this correct for current, okay? And direction of electron is anti-clockwise in the circuit, okay? So A is the correct answer to question number 25. That is settled. Question number 26. Which substance both contains large concentrations of free electron? Well, we know metals have large concentration of free electrons. They have abundance of electrons. So that will be the metals, aluminum and glass. This one has large concentration of free electrons, but glass is a non-metal. It does not have large concentration of free electrons. That's if it even has at all. It doesn't even have. Okay, if glass would have electron, it would be due to electrostatics, charging glass rod by rubbing it with silk, and those are not free electrons. So it doesn't have. Copper and water doesn't have. Copper and nylon doesn't have. Silver and gold, these two are metals, and metals have large concentration of free electrons. Number 27. A resistance wire of length L melts and has to be replaced with a wire of the same material and the same resistance. The resistance wire, okay, the first resistance material must have the same resistance as to the one you are using to replace it. Both of them must have the same resistance. Understood, right? Yeah, okay, let's continue. The resistance wire of length L. So resistance wire R1 has the length L. Let me just call it L for the first resistance wire, length L. It has to be replaced with a wire of the same material and same resistance. Good. So both of them must have the same resistance. The only wire available has twice the diameter of the broken one. So diameter of the second one would be twice diameter of the first one that got broken. Okay, so diameter, the only wire available, which is this one, okay, the one available has twice the diameter. So diameter of this second wire is twice the diameter of the first wire. Which length of the wire should be used? What length of the second material should be used? That's the question. Okay, so resistance, they have the same resistivity because they are both made of the same material. Okay, they have the same resistivity. Okay, what we just work with is the diameter. Okay, yeah, and remember that cross-sectional area A1 is pi d square over 4. Okay, that's diameter of wire 1, pi d1 square over 4. Okay, yeah, area is pi d square over 4. And cross-sectional area of the second wire is pi d2 square over 4. Okay, where d1 is diameter of the first wire that's cut, and d2 is diameter of the second wire that you're using to replace it. Now let us solve and get what L2 should be. Okay, good, let's go. Okay, now we have to bring in the formula for calculating resistivity. Since resistivity equal to Ra divided by L, like resistivity is resistance multiplied by area divided by length, and yeah, so we have to bring this formula into this expression since the resistivity of the two materials are equal. Okay, yeah, so since the resistivity of material 1, resistivity of the first fuse, okay, the first wire that broke, that will be R1 A1 over L1 must equal to R2 A2 over L2. Yeah, since the resistivity will be equal, okay, resistivity of the first wire must equal to resistivity of the second wire since they are made of the same material, right? Good. And you know, the two resistors, yeah, they are made of the same material, so they will have the same resistivity. And resistivity is Ra over L. Yeah, or you can express it in terms of um, resistance too, since the two resistors are expected to be equal. Okay, the two resistors are supposed to be equal. You can express it in terms of resistance. You know, R equals to rho L over A. Yeah, you can express it that way. That since R1 equals to R2, then you can also express it as rho L over A1 equals to rho L over A2. Okay, like rho L over A equals to L over A. Okay, so either you use this expression or use this expression. Either way you do it, you get the same answer. So let's continue. So from where we've gotten to, what we are looking for is L2, right? Let me cross multiply. Since R1 equals to R2, okay, I can just equate both of them as R. Instead of writing R1, R2, I can say R1 equals to R2 equals to R. So instead of having R1, R2, I can just write both of them as R to make my work easier. I want to make L2 the subject. What is L2? L2 equal to what? If I cross multiply, let me start by cross multiplying. If I cross multiply this way, what will I have? I will have L2 RA1 equals to L1 RA2. R is common on both sides. I can just cancel it out. So I'll be left with L2 equals to L1 A2 over A1. Yeah, L2 equals to L1 A2 over A1. What is A2 in terms of A1? A2, since area equals to pi d squared over 4, yeah, A1 is pi d1 squared over 4, A2 is pi d2 squared over 4. So I want to substitute that here, okay? So I have L2 equals to L1 multiplied by pi d1 squared over 4. And I'm dividing it by A1. How am I getting this? L2 equals to L2 equals to L1 multiplied by A2. What is A2? A2 is pi d2 squared over 4. So I put pi d2 squared over 4 here, okay? And I'm dividing this by A1. What is A1? A1 is pi d1 squared over 4. Pi d1 squared over 4. Okay, so we have a denominator of 4 on both sides. Okay, so we can remove the 4. Since we have it on both sides, we have pi, okay, I mean on the numerator and denominator. So you can remove those ones that appear on the numerator and denominator. So at the end, you'll be left with L2. Okay, length of the second material will be L1 multiplied by D2 squared divided by D1 squared. Do not forget, by diameter of the second material, D2 equals to twice the diameter of the first wire. Okay, so I have L1 multiplied by D2 equals to 2D1, okay? So instead of writing D2, I write 2D1, 2D1, okay? Do not forget that I'm to square D2, there's square here, so I have to square it. Then I'll divide it by D1 square. So this means we have L1 multiplied by 4D1 square, because 2 squared is equal to 4, okay? And I'll divide this by D1 square. D1 square is common on both sides. What can I do? I can cancel them out. So I'll be left with 4 times L1. That simply means the length of the second material should be 4 times of the length of the first wire, which makes option D the correct answer. Please, if you don't understand this explanation, make sure you watch this part of the video again. We go straight to question number 28. A teacher wishes to show the production of electrostatic charges. She holds a rod and rubs it with a cotton cloth. A copper rod, a glass rod, a plastic rod, and a steel rod are available. Which two rods would both be suitable to use? We don't use metals to produce static electric charges or electrostatic charges. Why? Because electrostatic charges are charges that rest, that are stable, they are not moving. So if you use a metal, a conductor, then the charges the charges will flow. It flows through your hand, through your body, and you won't be able to have the electrostatic charges on the rod. Okay, so should you use copper and glass? Copper is a metal, is a conductor. We can't use any conductor. Plastic and copper. Copper is a conductor. Plastic and steel. Steel is a conductor. Where do you have two insulators? Glass and plastic. B. Glass is an insulator. Plastic is an insulator. B. That makes B the correct answer to question number 28. We go to question 29. Two resistors with resistances R1 and R2 are used as a potential divider. What is the relationship between R1, R2 and potential differences V1 and V2? This is in line with the voltage divider principle. How does the voltage divider work? Question number 29. Two resistors with resistances R1 and R2 are used as a potential divider. What is the relationship between R1, R2 and the potential difference V1 and V2? Okay, and when you see potential divider, the Voltage will be divided in the same proportion as the resistances of the resistor. What do I mean? What I'm saying is V1 ratio V2 must be in the same ratio as the resistor R1 ratio R2. Okay, that simply means if the resistance here is higher than resistance here, it means the voltage here will be higher than the voltage across the second resistor. So that's this formula for the voltage divider. So from this, yeah, R1 over R2 equals V1 over V2. That's option D for question number 29. We go straight to question number 30. The diagram shows a light-dependent resistor (LDR) connected to a potential divider circuit. The brightness of the light falling on the LDR is increased. Which row shows what happens to the resistance of the LDR and what happens to the reading on the voltmeter? Okay, there's a light dependent resistor here. LDR means light dependent resistor. And how the resistor works is that when the intensity of light shining on this resistor is high, when the light is bright, the resistance of um, this component of a circuit here, this is a component of a circuit, and the resistance of this LDR will fall. When the light is bright, shining on it, when bright light is shining on it, the resistance will reduce, okay? But when the light shining on it is dull, the resistance becomes high. So now let's focus on the situation whereby the light shining on it is bright. Okay, when bright light shines on this, resistance will reduce. Do not forget that from the voltage divider principle, when the resistance here drops, it simply means voltage here will be lower. Okay, yeah, from the concept of voltage divider principle. Okay, when the resistance here is high, it simply means voltage here will be higher. Okay, will be high. And when the resistance here is lower than resistance here, it simply means voltage here will be lower than voltage here. If resistance here is higher than resistance here, then voltage across this resistor will be higher than voltage across this resistor and vice versa. So that same concept will be applied here, okay? Okay. What happens to the LDR? The brightness of light falling on the LDR is increased. When the brightness of the light is increased, what happens to the resistance? It will decrease. Resistance decreases, and reading on voltmeter, it will definitely decrease because voltage is decreasing. That makes A the correct answer to question number 30. We go to question number 31. A simple AC generator has a coil rotating in the magnetic field. What happens to the peak electromotive force (EMF) and to the frequency of the AC output when the coil is rotated faster? And you know, when you have a coil rotating in a magnetic field, and EMF will be induced, and the magnitude, okay, of the induced EMF depends on the speed of rotation. Okay, it also depends on the strength of the magnetic field, yeah, and the number of turns. Okay, but now let's focus on the speed. When the speed is high, then the peak EMF will be high, okay? When speed is high, then EMF will be high. Now let's talk about frequency. Frequency is the number of cycles produced in 1 second. And you know, these cycles of oscillation are produced by the rotation of the coil. So if you are increasing the speed, it simply means more cycles will be produced in 1 second. Hence, the frequency will increase. Frequency will also increase. That's what it means. Okay? Yeah, so the peak EMF will be greater and the frequency will be greater. That makes A the correct answer to question 31. We go straight to question number 32. A current passing along a wire placed between the poles of a permanent magnet. The wire experiences a force due to the magnetic field. What will change the direction of the force? Increasing the current? No, not increasing. Either you change the direction of the current, yeah, or you reverse the polarity of the magnet. Put south here, put north here. The direction of force will change. You're reversing the current. Good. When you reverse direction of current, direction of motion changes in line with Fleming's left-hand rule. You can try this out. You get it out. You get it right. Question number 33. What is a transformer used for? You step up the voltage, current reduces, and that way you minimize losses. Changing the direction of current, no. Changing the magnitude of alternating voltage, excellent. It changes the maximum of the magnitude of alternating voltage. Yeah, so if it is step up transformer, it steps up the voltage, thereby stepping down the current, okay, to minimize losses. And if a step down transformer, it steps down the voltage, thereby stepping up the current, okay. Yeah, and that is usually the case if it's for distribution, okay, for electricity to be supplied to houses and factories or companies that make use of it. Question number 34. The scattering of alpha particles by a thin gold foil provides evidence for the nuclear model of the atom. Two alpha particles of the same energy are incident on a nucleus of gold. Which diagram shows the correct path followed by the alpha particles as they pass close to the nucleus? Okay, remember Rutherford's experiment, okay, on the scattering of alpha particles that are directed towards gold foil. Remember? Of course you do. And if you do not remember, this simulation shows you the experiment Rutherford conducted. He had gold foil here, okay, and he had this gun that would shoot out alpha particles, okay. So when the alpha particles get to the gold foil, so we have this amplified um, view here, okay, for you to be able to visualize what is happening here properly. Okay, so I'll press this button, alpha particles come out. Okay, so here they are passing through this gold foil. So when they pass through gold foil, some of them pass through without being deviated, fine. But the ones coming close to the nucleus, this is a nucleus, what happens? They get deviated, okay? So when it's very close, the deviation will be much, but when it's not very close to the nucleus, the deviation will be minimal, okay? When it's far away from the nucleus, you won't even notice the deviation. But when it's close enough, not very close, but close enough, you see slight deviation, slight deviation. When it's very close, deviation will be pronounced, okay? Yeah, look at that one, okay? Deviation will be so pronounced when it's very close. So that's what we have here. So here, the one that is very close, deviation is maximum. The deviation is very high, okay? Yeah. And the one that is a bit further away, deviation is not as much as the first one. So this is correct. Okay, look at this one. Will it move in circles like this? If it's moving this way, then it means the nucleus is attracting the alpha particles, but no, the nucleus repels alpha particles because alpha particles are positively charged and the nucleus of gold is positively charged, so there will be repulsion. So this is the only one that shows the correct order. Here shows that the closest one experiences less deviation, and that is wrong. The closest one experiences higher deviation than the one further away from the nucleus. This is the case if there was attraction between alpha particles and the nucleus, then they will follow this path. But that's not the case. There's no attraction, there's repulsion. So this is the only correct one, option A. Number 35. The half-life of carbon-14 is 5,700 years. An object containing carbon-14 has count rates of 100 counts per minute when it is first formed. The graph shows how the count rate decreases over time. Now let us look at the graph. So the graph shows us the initial number of elements, the initial count rate, okay? Count rate was initially 100 counts per minute, okay? And it began to decrease to 75, sorry, to 75 years, 50, no, that's not the order. This should be what we have here, okay? Yeah, then this should be what we have here. Okay, I think this should be what we have here. Fine. It's fine. So if this is 100 and this is 50, then it means the time taken to go from 100 to 50, this should be 50, this should be 25, and this 0. That means the time taken for the count rate to go from 100 to 50 is half-life. Automatically, this is half-life. Now the question, which point on the graph corresponds to a time 11,400 years after the formation of the object? After the formation of the object, okay, you know this is the half-life, right? So after 5,700 years, okay, so this should be 5,700 years half-life. After 5,700 years, what will be left? You'll be left with 50 counts. But now they are asking you that which point corresponds to 11,400 years. So let's see 5,700 plus another 5,700, okay, another half-life now. That will be 11,400. Okay, so that simply means after another T half, After another T half, which should be around here, this is the number of elements that we left, 25. Okay. Yeah, that simply means D is the one that corresponds to 11,400. Okay. Yeah. Every half-life, the number of elements will be halved. After another half-life again, the number of elements will be halved. Okay. Like divide 50 by 2, you get 25. 25 will be left. If the graph was to continue, after another half-life, the number of elements left will be half of 25, which will be 12.5. Okay. So if the graph was to continue, it will go this way and go that way, on and on and on and on and on. So that is how you solve questions on half-life. Okay. So that simply means D is the one that shows this 11,400 timestamp. Okay. Yeah, if it's not clear, you may watch this part of the video again, please, so that it's become clear to you. It's very important that all of this is clear to you. We go straight to the next question. Question number 36. Why are beta particles deflected more strongly than alpha particles when they enter an electric field? Okay, so imagine we have an electric field here. Okay, these are positive plates and these are negative plates. Okay, yeah. So now if alpha particles enter an electric field, alpha particles, let me use color green for alpha. If alpha particles enter an electric field, what happens? If they are coming this way along this straight path, they'll be deviated this way. Why? Because alpha particles are positively charged. Okay, alpha particles are positively charged, so the electrons will attract them. The negative plates rather would attract the alpha particles, while the positive plates will be repelling the alpha particles. Okay, yeah. So let me draw a more realistic diagram. So they'll be deflected slightly actually. But let me use color red for electrons. If they were beta particles, which are electrons, beta particles will go this way and they'll be deflected towards the positive plate. And the deflection of beta particles will be more than that of alpha particles. Why? Because of the mass. Alpha particles are massive, alpha particles are massive, while beta particles have tiny mass or negligible mass. The mass of the beta particle, mass of an electron, is negligible when compared with the mass of an alpha particle. You know, alpha particle is 2 protons and 2 neutrons. Yeah, that should be like 4 units. While that of a beta particle will be 1 over 1,300 and, sorry, 1,735. Okay, mass of the electron will be 1 over 1,735 of the mass of a proton. Okay, yeah. So that means alpha particle will be 1,735 times 4 times heavier than the beta particle. Yeah, alpha particle is 1,735 times 4 times heavier than beta particle. That's why beta particle would easily be deviated. They experience more deviation, while alpha particles experience slight deviation. So if alpha particles are going this way, deviation will be so minimal, so small, unlike that of beta particle that is so obvious. Okay, and since beta particles are electrons, negative charge, okay, so they will be attracted towards the positive plates. That is what happens when you have alpha particles moving through an electric field and you have beta particles moving through an electric field. So which is the correct answer to that? Beta particles have less mass than alpha particles. A is the correct answer to question 36. A. Why did I switch to green? Okay, we go straight to question number 37. Oh, sorry, I have to remove all of this so that it does not lead to any form of distraction. All right, question number 37. Let's go. Which statement describes how nuclear energy is released by fission in a nuclear power station? When you see fission, just consider this I as what is splitting a heavy nucleus into two. Okay, But when you hear fusion, consider this U to mean the union of two smaller nuclei to form a heavier one. Okay, so fusion means the coming together of two smaller nuclei to form a heavier nucleus. While fission means the splitting. Consider this I to be this one, that is splitting. Splitting of a heavy nucleus to form two smaller ones. Okay, so let's see. Which statement describes how nuclear energy is released by fission? Fission, that's the splitting of a heavy nucleus. Atoms join together to make molecules. This chemical reaction, atom and molecules. Heavy nuclei splits into lighter nuclei. B is the correct answer to question 37. Okay, a heavy nucleus would split into two smaller or two lighter nuclei. Yeah, so that is that about that. We go straight to question number 38. Question 38. Oh, that was too much. Question 38 says, the diagram shows a star S and the initial arrangement of three planets X, Y, and Z. Each planet orbits clockwise in a circle about S. Each planet orbits in a clockwise direction. The time for one orbit of Y is 3 times the time taken for one orbit of X. So the time taken for Y to go around this star once is thrice the time taken for X. That means if X goes round once, Y would not have gone round once. Why? Because the time taken for Y to go round is thrice the time taken for X to go round. Okay, so if Y goes round once, X would have gone round thrice. And if X goes round once, Y would have just gone to 1/3. Okay, not even half, 1/3. Okay. By the time X is going around again, Y would have covered another 1/3 of its journey. By the time X goes around the third time, Y will now cover the third 1/3 of its journey. Okay, so that's it. But let's focus on only one going once. Then the time taken, the time for one orbit of Z is twice the time for one orbit of Y. The time for one orbit of this one is twice the time for one orbit of Y. What does that mean? That means if Y goes round once, Z would have just gone to half, because the time taken for Z to go once is twice the time taken for Y to go once. So for Z to go once, Y must go round twice. Are you with me? So if Y goes round once, Z would have just gone up to half. And if Y goes round up to this level, 1/3, then Z will just go up to half of that. Z will just have gone up to this level. You get it? Yeah. Now they're asking, starting from the initial arrangement, which diagram shows the position of planets after X has made one complete orbit? If X makes one complete orbit, then Y would have made 1/3 of that, then Z would have made half of what Y is making. So this, okay, so this position here for Z, this position here for Y, and this position here, sorry, this position here, yeah, and this position here for X, yeah. So this is the most correct answer to that question. Okay, yeah. Which option is that? A, B. Okay, let me have a second look at this question, please. Yeah, that's it. What we've done is correct. And which diagram is that here? Is that C? Y is there? No, Y should be here. That is B. Okay, X. Okay, X has gone around once. Okay, Y has just covered a third. This is Y. Y has covered a third and it's here. Okay, here. What about Z? Z would have covered half the distance of Y. So Z would have just gone from here to here. So that is what happens. Okay, yeah, and that's um, imitates how the planet orbits the sun. Okay, the one closest to the sun travels fast. Okay, this one would have done so many oscillations, while the one at the extreme ends are still trying to complete an oscillation. Okay, So Mercury would have done so many oscillations, while Venus would have done, while Venus will still be lagging behind, trying to complete one oscillation around the sun. So that's just the concept. Number 39. The nearest star to the sun is about 4 light years away from the Earth. A student makes 3 statements about the star. Light from the star takes about 4 years to reach the Earth. Yes, approximately 4 years to reach the Earth, because the Earth is close enough to the sun when compared with 4 light years. So this is correct. Number 2, light from the sun takes about 4 years to travel to the star and back to the Earth. Light from the sun takes about 4 years to travel to the star and back to the Earth. No, no, that will be 8 light years. Okay, because it will take 4 light years to travel to the star. Then if it's coming back to the Earth again, then it take another 4 light years. That will be 8 light years. Let's look at the third one. The star is outside our galaxy. Of course, the star is outside our galaxy. 4 light years. That is outside our galaxy. So that makes number 1 and 3 to be correct, which is option B. That makes option B the correct answer to question number 39. So, we have picked those two answer. Light from the star takes about 4 years to reach the Earth. That's fine, because it was said that the Is it a mixed force? Okay. The nearest star from this, the nearest star to the sun is about 4 light years away from the Earth. 4 light years. Yeah, 4 light years. That means it takes light 4 years to travel from that star, to the sun. Okay, so it takes 4 years. It takes 4 years. So for light to travel from that star to the sun. Okay, yeah. Light from the sun takes about 4 years to travel to the star and back to the Earth. No, no, no. Light from the sun takes 4 years to travel to the star, another 4 years to travel back. That will be a total of 8. Then the star is outside our galaxy. If the star outside our galaxy itself is made up of billions of stars. So many stars are in our own galaxy, our Milky Way galaxy. So if the closest one to the star, to the sun, is 4 light years, then it simply means it's just one of the so many stars that are in our own Milky Way galaxy. And by the way, the diameter of our galaxy is 100,000 light years. Yes. So it takes light. Okay, let's assume light is coming from the sun. Okay, light is coming from the sun and is traveling outside our galaxy. It will take this light 100,000 years before it can go outside our own galaxy. Okay, yeah, it will take the light 100,000 years to go outside our own galaxy. So if this star is just 4 light years, then it means the star is within our own galaxy, okay, our Milky Way galaxy. So this one is not part of it, okay. The star is not outside our galaxy, and light from the sun, light from the sun would not take 4 years to and fro. No, it can only take 4 years too. So that makes only number 1 is the correct one. And which option is that? Option C. And the last question, question number 40. A planet orbits the sun with orbital period T. Period, that's the time taken for one oscillation. So the time taken for one oscillation is taken as T. Fine. The average radius of orbit is R. Radius of orbit is R. Fine. What is the average orbital speed? What's the formula for speed? Speed is equal to distance divided by time. And what will be the orbital distance of this planet? The orbital distance of this planet, take note that the planets around the sun, let me erase all of this. The planets around the sun, they move in what? In circular paths, okay? Fine, they move in elliptical orbits. Elliptical. But you always approximate this elliptical orbit to be circular orbit, especially when the sun is in the center of the circular part. Okay, so you can use the formula for circumference of a circle. You know, this circular part is the circumference of this circle. Yeah, so the formula for circumference of a circle is 2 pi r, and you multiply it by the time taken. And do not forget that, yeah, the time taken here is the period. So we have 2 pi r. What's the radius of this circular part? That's the distance. This radius here is the distance between the planet and the sun. So we put d in place of radius, and we put period in place of time, because the time taken is period. And the radius of the circular orbit is the distance between the planet and the sun. So 2 pi d over t. Where do you have 2 pi d over t? Oh, sorry. You were told to take the radius as r, is not d. So the radius is r, not d. 2 pi r over t. Where do you have 2 pi r over t? I think that's option B. There are 2 pi r over period. So that brings us to the end of this question, okay? So past questions like this help you to quickly revise the entire syllabus. Ensure you keep practicing like this, and do not forget to subscribe to Physics for Everybody. See you on the next video. I wish you excellent grades in your examination. Do have a nice day. Goodbye.